Hello, my name is Dinko Klobuchar and this is Eurorec tutorial Comparators selecting voltage ranges. Let me explain what's the idea behind this tutorial. Let's say we have some signal, like LFO for example, and we want this LFO creating 3 separate pitch CVs to control 3 voices. I also want to be able to control boundaries of 3 voltage ranges. For example, green region would create pitches for bass voice, blue region would control second voice, and red one would be used for the third voice. You could achieve something similar with usual switch module with CV output addressing, something like this. Or if you attenuate main voltage source, you could achieve something like this. In that case, you will get equally spaced boundary points. But I want to be able to set boundary points at specific voltages. In this tutorial, I want to show implementation of this idea using comparators. But let's firstly go through the basics of using a comparator. We will use static voltages from 2 channels of pressure points and visualize it using data. Green channel is going to be controlling the first input of comparator, and blue channel the second input of comparator. Let's bring up attenuators all the way up, because we want to use exactly the same signal which is shown on data display. Comparator output will be visualized on red channel, and analog sum output on yellow channel. For now, I will set offset to be 0. To do that, we can use analog sum output. The signal is created by subtracting the voltages from 2 inputs and adding offset value. So if we provide 0 for both inputs, analog sum would be the value of offset. Now when offset is zeroed out, we can start testing voltage comparison. I'll turn off yellow channel for now. Bring the first channel voltage up a bit, somewhere around 2 volts for example. Let's turn on the red channel on data so we can monitor comparator output. We can see that when first voltage is higher than the second one, main comparator output is high. If we bring up the second voltage, so it becomes higher than the first input voltage, main comparator output goes low. Let's move the green channel a bit. Whenever first voltage is higher than the second voltage, comparator output will be high, and otherwise it will be low. There is also inverted comparator output, which outputs the opposite results. Let's also see what is happening with analog sum output. When we increase voltage of first channel, analog sum output follows. And as we increase the second channel voltage, analog sum starts dropping because second channel is subtracted from the first channel. You can also notice that comparator state changes always when analog sum crosses 0 volts. If we move offset value to some negative voltage, you will notice that the state changes, even though the second blue voltage didn't become larger than the green one. To avoid confusion, it is very important to understand this if you are using an offset. It is better to say that this comparator unit changes its state when analog sum crosses 0. This also means that we can use comparator with only 1 voltage and detect when it's higher than some value. To do that, we can remove the second channel input. I will set offset value to about -2 volts. Now when we increase the input voltage, we can detect if it is higher or lower than 2 volts. I want to show one more thing. Remember when I said before that comparator changes the state when analog sum crosses 0? Well, that's not completely true. Let's set offset value to exactly -2 volts. And start increasing the first input voltage to see when the state changes exactly. So we are now at 0 volts and state change at about 0.11 volts at some output. Let's go down. It changed at -0.13 volts. This is called a gap. To make it more obvious, we can increase gap control and do the same thing again. Now it changed at 0.75 at some output while going up. And it also changed at -0.75 when going down. This gap control can be very useful in many creative ways, but I was wondering about the gap when gap control is set to 0, so I reached out to Dieter Deufer and asked about it. This was his response. Reducing the gap to 0 would cause high frequency noise or multiple spikes when incoming voltage is the same as threshold voltage. That's why there is still small gap even when the control is set to 0. You may modify the module by removing 120k resistor to obtain 0 gap, but I do not recommend that because of the mentioned behavior. Equipped with this knowledge about comparators, we can start building our system to split LFO signal at specific voltages. Firstly, I want to set comparator offsets to some specific values, so we can easily test the results. The first one to -2.8, and the second one to -5.6. Let's say that first voice should be generated by LFO section from 0 to 2.8 volts, and second voice from 2.8 to 5.6, and third voice will be anything above that. I'll zero out the polarizing mixer as well. Let's use pressure points as our main voltage source for now. Later it will be replaced with LFO signal. We will need copies of main voltage source, so I will use buffered mult for better precision and connect the copies to both comparators. We will want to monitor this main voltage, so I'll run it through data before anything. Increasing the main voltage should change state of comparators. When it increases above 2.8 volts, comparator 1 changes the state to high. When it passes 5.6 volts, output of the second comparator also switches to high. That is all the information we need to select between ranges of the input signal. Since comparator outputs are discrete values, low or high, you might be tempted to use some logic modules to find out when you are at specific range, but there is much easier way to implement this. What I want to do is add those voltages together and make them equally spaced, so I can use them as control for a switch module. Of course, adding voltages of 10 volts would be clipped, so we need to attenuate them first. Let's make them 1 volt for simplicity. Increase the main voltage until the first comparator output goes high. At this state we want mixer output to be 1 volt. And increase main voltage again until the next comparator goes high. Now when both comparators are high, we want mixer output to be at about 2 volts. We can now use mixer output as control voltage for sequential switch matrix. Any switch with CV controllable output selection can be used. Changing the main voltage changes between 3 different sequential switch matrices. I will attenuate CV input a bit more to make it use first 3 matrices only. And that would be index 0, 1 and 2. You can also see that comparator LEDs light up in sync with matrix selection change. We can now switch main voltage source between 3 outputs at voltage levels we defined on comparators. I'll connect those 3 outputs to data so we can monitor results. Let me offset main voltage display so we can see it separately. Now I want to replace manual voltage from pressure points with LFO signal. I'll use basic waveforms for now. I also want to modify this signal so it is in positive range and attenuate it properly. Now we can clearly see the switches happen. Let's also set some cursors to show that this is quite accurate. First cursor at 2.8 and second one at 5.6. We can test few different waveforms and frequencies. And it looks like everything is working correctly. This is a nice visualization, but if we want to create pitch CV for oscillators, this is not so useful. The signal appears to be split on screen, but it is continuous signal and goes to 0 when output is not passing the input voltage. Rather than switching LFO signal, we can switch gates that will trigger different quantizer channels and use continuous LFO signal as quantizer input CV. Let's create clock CV and pass that to sequential switch. Looking at data display, you can see some problems appearing. Some clock gates are cut and split into different outputs. This is because our main LFO will often switch comparator states during the clock gate. Since we will play our melody in some tempo, we can easily fix this by sampling main LFO signal at that clock rate. We just need to run our main signal through sample and hold module. I also want to keep continuous signal at display. I'll just insert sample and hold after data display. And trigger will be our main clock. And as seen on data, we now have much cleaner result. Let's now pass those gates to Quantizer. And Quantizer gates will trigger 3 envelope generators. Let's get LFO signal that will be used to create pitch values. I want some additional control over that signal, so I am passing it through offset and attenuator module. This will enable me to offset and modify the range of pitch values independently of the main comparator signal. So comparators will always stay very accurate in full range, while I could be, for example, generating melodies within 1 octave or in the range of 1 volt. And now we can hook up our oscillators and VCAs. Off screen I have very simple setup. Just 3 oscillators running through VCAs, and all are mixed through one filter and then processed by black hole DSP. Very simple, just basic waveforms and some FM. Now you can hear that some more strange things are happening. The problem is synchronization of all those events. Like for example, comparator change controlling switch, the same clock signal sampling LFO and triggering Quantizer at the same time. To avoid any synchronization issues, we can slightly delay clock signal triggering Quantizer. So Quantizer gates will be a little bit delayed. Trigger delay didn't fit into this case, so I will use envelope generator to offset this trigger slightly. You can see the changes I am making on the scope. Rising edge of the clock has some slope now, so it takes a bit of time to get to level that would be considered a trigger level. I have set decay and release to 0 and sustain to full to keep level at maximum. And our sync problem is gone now. And we can now play a bit with the system. All examples are really basic, very basic sounds just to demonstrate the concept. In conclusion, we built a flexible system that creates pitch data for 3 voices from single LFO. This can easily be expanded to create more voices if you add more comparators. Using second comparator input, you can also control and animate breaking points over time. To create loops, sequence the system like this, or add different kinds of variations, take a look at my previous videos. Thank you for watching.